Hey guys, here's another example of a heat transfer problem. In this one, we're going to heat water through its boiling point and then into steam, and then raise the temperature of that steam to 200 degrees C. So we've got a little bit of work to do in a problem like this. The first thing we want to do is write out all the equations that we're going to need. And that's going to consist of a term to heat the liquid water from 40 degrees to 100 degrees C, and a term that involves the heat of vaporization of water so that we can convert all that liquid at 100 degrees to gas, and then a term that heats the steam from 100 degrees to 200 degrees. And we'll handle that in 3 steps, 1, 2, and 3, just like this. Now, because each of these terms contains the mass, we can factor the mass out to make this a little bit easier. And then we can just start plugging in our values. All the thermodynamic data for water are on the lower left. Now, the mass of 100 milliliters of water is roughly 100 grams. That's because the density of water is 1 gram per milliliter. The heat capacity, or the specific heat of liquid water, is 4.184 joules per gram C, and the temperature change is 60 degrees C, 40 to 100. The heat of vaporization of water is very large, really, for a substance, and that is 2,260 joules per gram. And the heat capacity of gaseous water is quite a bit lower than for liquid water, 1.996 joules per gram. And the temperature change there is from 100 to 200, so it's 100 degrees C. So we put all those things together, 100 grams times everything that I've written here. We'll just kind of organize this a little bit more. I think it's always a good idea to write out the formula and then assign the numerical values that you have to each of the components of the formula. It's just a way to make fewer mistakes. So I'm using a shorthand here. All the terms within those brackets should have units of joules per gram. And so if I just multiply 100 grams by those terms, let's multiply them out. 251 joules, 2,260 joules per gram, and 199. Notice that the vaporization term is by far the biggest contributor to the energy that needs to go into this system to raise this temperature. So here's our sum, and then we'll multiply that by 100, canceling the gram units there to get units of joules. Whoops, it looks like I accidentally multiplied by 1,000 instead of 100, so that really should be 271 kilojoules of energy needed. Sorry about that, it happens.